All right, a square has side A, perimeter 4A, area A squared. Consider all rectangles of constant perimeter 4A. Given that X is one side of the rectangle, show that its area is given by that. Okay, so we have a rectangle with side lengths X and Y. So the perimeter is 2x plus 2y, and that's going to be equal to 4a. And we have to make it look like that. Okay, so if we take this, we're going to have p okay, no, we'll solve this one for y. So 4a minus 2x over 2 is y. So that's 2a minus x. And that's what y is equal to. So that means the area of that is x times 2a minus x. And that's 2ax minus x squared. Given that one side of the rectangle is a over 2, find its area. So same kind of situation. We're going to have a over 2 and y. So we're going to have 2a over 2 plus 2y is the perimeter, and it's still equal to 4a. So this is a plus 2y is 4a. So y is going to be 4a minus a, 3a over 2. So 3a over 2. So the area here is a over 2 times 3a over 2, which is 3a squared over 4. Okay. Show that the rectangle of maximum area is the square with the area of the max equals a squared. Justify your answer. So I'm not entirely sure which one they're talking about. So if we do this one, dA dx, that's 2a minus 2x equals 0. So 2a is 2x, so a is x. And so at x equals a, and then the area would be a squared. And then we'd need the second derivative with respect to x. So it's just negative 2, which is less than 0, which means at x equals a, it's a max. If it's this one, okay, we can't use that one because there's no x. Okay. All right, B. Consider all rectangles of constant area a squared. Given that x is one side of the rectangle, find expression for the perimeter. Okay, so we've got x and y. So the area, which is a squared, equals x times y. So y is a squared over x. So the perimeter is 2x plus 2a squared over x. And then given one side is a over 2, so we have a over 2 and y. So a over 2 times y is a squared. So y is going to be 2a. And then we have the perimeter is twice a over 2, which is a, plus twice 2a, which is 4a, so 5a. And now we want to show the rectangle of minimum perimeter is the square. All right, so we want to use the one with x, this one. So we're going to have 2 plus, well, actually minus 2a squared over x squared. And when we set that equal to 0, we're going to have 2 equals 2a squared over x squared. 2x squared equals 2a squared. X squared equals a squared, so x equals a. And so we have that when x equals a, the perimeter is a minimum. So the perimeter would be 2a plus 2a squared over a, which is going to be 4a. And then we would need the second derivative to justify. So that's going to be, because this would be 2 minus 2a squared x to the negative 2. The 2 goes away. So we're going to have 4a squared x to the negative 3. And when we sub in x equals a, it's going to be greater than 0. Okay? So that's concave up. There's a min at x equals a. Okay, consider all closed cylinders, height h, base, radius r, constant volume v. So that means v is pi r squared times height. Express the surface area. So that's 2 pi r squared, top and bottom circles, plus 2 pi r h. And express total surface area S of the cylinder in terms of V. Pi r squared h. So we want it in terms of V and R, so we have to solve this for h. So this is V over pi r squared. So S is going to be 2 pi r squared plus 2 pi r V over pi r squared. So 2 pi r squared plus 2v over r. Now ds with respect to r. So that's going to be 4 pi r minus 2v over r squared. Hence, show that the radius, so we want a minimum, so we have 0. 4 pi r equals 2v over r squared, and multiply by r squared, 4 pi r cubed, divide by 4 pi, so v over 2 pi, and then we're going to have to the 1/3. Okay, justify, it's a minimum, so d second derivative is going to be 4 pi, the r drops, plus 4v over r cubed. And then we want to substitute r in there. V over 2 pi to the 1/3 cubed is, the cubed goes away, so we're going to have v over 2 pi, so we flip. Well, it's greater than 0, isn't it? So greater than 0, so that means it's concave down, so minimum there, okay? Do there exist cylinders of maximum total surface area? So since the second derivative is always greater than 0, there's always a minimum, but there's no maximum. Okay, consider all closed cylinders of height h, base r, constant surface area s. So surface area is 2 circle areas plus 2 pi r h, and volume is pi r squared times the height. So we need to solve this for h. So we're going to have s minus 2 pi r squared over 2 pi r, that's h. So now we have v is pi r squared, s minus 2 pi r squared over 2 pi r. And the pi's will cancel. One of the r's will cancel. So we have, if we distribute the r, we're going to have rs minus 2 pi r cubed, and each of these is over 2. Now we want dv dr. So that's going to be s over 2 minus, these cancel. So then we have minus 3 pi r squared, hence show the radius. Okay, so set this equal to 0. S over 2 is 3 pi r squared. So s over 6 pi to the 1/2 is r. Okay? Justify there's a... So we need the second derivative, which is just going to be negative 6 pi r. And when we substitute s over 6 pi to the 1/2, well, this bit is always positive, so this is always less than 0, which means it's concave down, and there's a max at that r. So do there exist cylinders of minimum volume? So the second derivative's always less than 0, but at some point the volume goes negative. So that doesn't make any sense. So that's where the minimum volume exists. So if we set that volume equal to 0, we have rs over 2 equals minus pi r cubed equals 0. So if we factor out an r, that's going to be s over 2 minus pi r squared equals 0. So we're going to have r is 0 here, or s over 2 minus pi r squared equals 0. So divide by pi and square root. So at those two values, that's where the volume equals 0. So that's where it's going to have the minimum volume.